Welcome. After learning about the various estimation methods for the thermodynamic properties and the combustion properties, in this particular tutorial, in this lecture, we shall see some tutorial to use those methods to find out these properties. So, this particular lecture is on the estimation of the thermodynamic and combustion properties. So, what we shall learn in this lecture are to estimate the specific heat capacity, thermal conductivity, VOC number and CARI, that is the combustion air ratio index, by with some specific example on a natural gas. Now, we see the statement of the problem. It is like this: we have a natural gas with this particular composition at this pressure 6000 psi and 150 degree Fahrenheit. Now, this particular composition was also considered in the previous lecture, where we were finding out the thermophysical properties of the natural gas, and we have kept the same composition because we will find that some properties will be taken from the earlier lecture in this problem too. So, in this we have been given the high heating value of the natural gas as 1050 BTU per cubic feet and the air to fuel ratio as 12.56. With these data, now we proceed to go for a solution. Now, before we go for the solution, we do some unit conversions, because some of the units in the correlations are not in FPS system, they may need the SI unit. So, we are putting both the SI as well as the FPS units. So, here we have that first we convert the PSIA into MPa, from knowing this, that 1 MPa is equal to 145 PSIA, and then we convert temperature in terms of Kelvin. This is given in Fahrenheit and we make it in Kelvin. And after doing these unit conversions, we go to the estimation of the specific heat capacity. We showed this particular expression earlier, and in this expression we have some parameters J and K. Again, we find these parameters are given in terms of many other parameters, J1 up to J8 and K1 up to K8, and when here we have the mole fractions of H2S, carbon dioxide, nitrogen and the specific gravity of the mixture. This specific gravity we found out in the earlier lecture for the same composition of the natural gas. That is why we kept the composition same. So, again we have another parameter K, and which is again given in terms of K, K1, K2, K3 etc., which are associated with the mole fractions of the H2S, CO2, nitrogen etc. Now, this is the table which gives us the value of these Ji's and Ki's, and for this expression what we do, write the mole fractions, the Ji values, and take these products of Jiyi and Kiyi, and the gamma mix and is taken here from, and then we find that this is the summation of the Jiyi and the summation of the Kiyi. And here we find the pseudo critical pressure and temperature by this formula. So, we take this K square value and this J square value from these tables, and we find out the from this formula we find out the value of this. Please understand that K and J, they are the average values, that is why we needed to do this summation. So, they are average Ki, that is this, and this is the average Ji, that is this. So, we put this, plug in the values to get the values of the pressure and pseudo critical temperature, pseudo critical pressure, and with these are the units. These are given in terms of megapascal and Kelvin. So, we needed to convert the units of the given data to Kelvin and megapascal, and here we have the pseudo reduced pressure and pseudo reduced temperatures. Now, after knowing this, we find the values of these parameters A and B, and in this we have this beta given in this is given from this expression, and here we have the values of the various other parameters beta 1, beta 2, beta 3, beta 4, beta 5 from this table we plug in, we get the value of beta, and this beta is taken to find out the value of A. So, now we come to the solution of this particular expression Z. We shall be using this value of the compressibility factor, and when we put this value of A, B, etc., we find that we get this value of Z here. Now, please understand, this is a cubic equation. We have not shown the details of the solution of this cubic equation of state, but there are 3 solutions here, and if you do this calculation, you will find that the 3 solutions may come to real. Now, we take the maximum value of the Z for the vapor phase. So, this is how we are getting the value of Z as 0.9461 by plugging in the values of these A and B in this expression. And after this, we find this value of this small a and small b in terms of the pseudo critical pressure and temperature. And here we have that this expression d beta by dt, and this d beta by dt is given by this expression, and we put this, make use of this table given here to find out the values of these various parameters beta 3, beta 5, beta 6, etc. And we get the value of the various derivatives of the beta with respect to temperature as this. So, after getting these derivative values, we go to find out the value of 2 more parameters m and n in terms of this z, and then we come to the expressions or the correction factor. This is given by this expression, and in this expression we have this beta b1, b2, b3, etc., which are taken from this particular table. And again in this we have another Cp naught, which this Cp naught is given in terms of the A1, A2, etc., which is taken from this particular table, and then we get the value of the Cp naught as this, and ultimately we get the Cp naught for the ideal gas, and for the real gas we apply the correction factor to the ideal gas Cp, and we get this particular value as joule per mole per Kelvin by inputting the various parameter values. Please understand that these expressions are to be taken from the literature, and there is no need for memorizing these expressions. Only thing is that we have to have the various parameter values available to us to calculate these various parameters, and we find that all these parameters are depending on the temperature, pressure and the composition. Now, after this we come to the estimation of thermal conductivity. This is one expression given, and in this we find that this thermal conductivity depends on the thermal conductivity at 1 atmosphere. So, first we shall see how to estimate this conductivity at 1 atmosphere, to which we put some correction factor to get the actual thermal conductivity. So, here we have a chart. In this chart we have this value of the gamma, and this value is 0.69, and then we go to the, this is the pressure given, temperature given to us 150 degree Fahrenheit. So, at this temperature for this particular gamma we read out the value as about 0.028 for this lambda 1 atmosphere. So, we put in these values in this particular expression, and then we have been given this particular chart, and in this chart we get the value of the A9, A10, A11, and these we plug in to get the value of the thermal conductivity as 1.13 BTU per feet per hour per Fahrenheit. This is as per the correlation. Now, we have another correlation for finding the VOC index, which is definition, that the definition is goes like that the ratio of the high heating value to this specific gravity, and here we have the rho g as 333 kg per meter cube, which can be obtained from our earlier tutorial on the thermophysical property measurement, and here we have the density of the air, and this value has been given in the problem. With these values, we find out the VOC index to be 11886 BTU per cubic feet. After finding VOC index, we go to estimate the value of the combustion air ratio index from the air to fuel ratio. Here is the formula that we use and we plug in the values of the given natural gas, and we find that CARI is coming to be 15. Now, these are the references which we referred to, and this has been also given in our earlier lecture on the estimation of these properties, from which we have taken the correlations and the various tables for the various types of parameters. Thank you.